Have you ever actually stood at the base of a massive dam, looked way up at that towering wall of concrete, and wondered how on earth this thing's surviving? Right behind that wall is this invisible, relentless giant of hydrostatic pressure. We're talking millions of gallons of water, weighing millions of tons, constantly pushing against the barrier. Well, today, we're going to unpack exactly how engineers understand, calculate, and ultimately tame that invisible giant, all so that a relatively simple wall can hold back an entire lake.
Welcome to this explainer. I am super excited to get into this one with you today. We're looking at hydrostatic forces on surfaces. And whether you're a hardcore engineering enthusiast or just someone who kind of loves understanding how our built world actually works, this explainer is designed to give you a really clear, direct path to understanding fluid mechanics. We literally rely on these exact principles every single day to keep our infrastructure safe. I promise, by the end of this, you're going to see water and dams in a completely different light.
Okay, let's dive right in. Here's a quick look at what we're covering today. We'll start with the weight of still water, move on to calculating total pressure, figure out how to find the center of pressure, look at forces on curved surfaces, and wrap it all up with engineering gates and dams.
Starting with Section 1, the weight of still water. This is where we establish the baseline rules.
So, before we can even think about building a dam, we have to understand the absolute baseline rules of the fluid we're trying to contain. And it all starts with this fundamental definition. A fluid at rest is in a state where the shear stress is exactly zero. Now, what does that actually mean for us? Well, shear stress is the force that causes layers of fluid to slide past one another. Think about water flowing rapidly down a river. That's a lot of shear stress. But in a static tank or a perfectly still lake, the water isn't sliding against itself. The fluid is completely locked in place, theoretically speaking anyway. And this total lack of shear stress, that is the foundational characteristic of hydrostatics.
And because there's absolutely no shear stress, a static fluid cannot exert any sideways sliding force along a wall. It just can't. It can only push straight on. Therefore, all force exerted by a static fluid must be perfectly perpendicular, or normal, to the surface it touches. This is an incredibly powerful rule to keep in mind. It means whether a surface is flat, angled, or totally curved, we always know exactly the direction the water is pushing.
Moving right along to Section 2, calculating total pressure.
Now, knowing the direction of the force is great and all, but engineers need hard numbers, right? They need to know the magnitude. So, imagine a completely flat, irregularly shaped plane that is totally submerged underwater. There are two really important points to think about here. The first is G, which stands for the center of gravity of the shape itself. And then we have H bar, which represents the depth of that exact center of gravity straight down from the free surface of the water above. Believe it or not, this remarkably simple setup is the whole key to figuring out the total force crushing against this plane.
And here is the elegant little formula that solves it. F equals rho times G times A times H bar. Let's break that down real quick. Rho is the density of our liquid. Water is heavy, so obviously density matters a lot. A is the total area of the immersed surface, and H bar, like we just mentioned, is the depth of the center of gravity. It's that simple. You just multiply the area of the wall by the depth of its center of gravity and the density of the fluid, and boom, you've got the total absolute force pushing on that surface. But here's the catch. Knowing the total force isn't quite enough to stop a wall from tipping right over.
Which brings us to Section 3, finding the center of pressure. This is all about where that force actually focuses.
Okay, so we know how much total force is pushing against the wall, but where exactly is all that force focused? This is a crucial distinction. The center of gravity is really just geometry. It's the physical center of the shape itself. But the center of pressure, that is the exact specific point where we can imagine the entirety of the water's pushing force is concentrated. And here's where it gets kind of mind-bending. Pressure increases the deeper you go into water, right? Because the bottom half of a submerged wall is deeper than the top half. The bottom half gets pushed much, much harder. This imbalance actually drags the average point of pressure downward. So as a result, the center of pressure is almost always lower than the physical center of gravity.
If you look at an inclined surface immersed in fluid, you can clearly see G at one depth, and then right below it is P, the center of pressure. Engineers use the variable H star to represent this exact depth from the water surface down to this critical center of pressure. Think about it. If you're designing a massive support strut to hold up a retaining wall, you don't aim it at the physical center of the wall. No way. You aim it precisely at H star, where that invisible giant is concentrating its entire push.
To find that exact depth, engineers use these formulas. Now, don't let the math scare you off here. Let's just focus on what it tells us about the structure. Notice IG in those equations? That stands for the moment of inertia, which deals with exactly how the shape's area is distributed. The big takeaway here is that calculating H star requires knowing the shape of the wall, its angle, and its depth. But as a super handy shortcut, if you just have a simple flat vertical wall resting on the bottom, the center of pressure always hits exactly at 2/3 of the total depth of the water. Pretty neat, right?
All right, Section 4, Forces on Curved Surfaces. Time to bend the rules a bit.
So, everything we've talked about up to this point assumes a perfectly flat wall. But what happens when our surface isn't flat? What if it's curved? Calculating forces on a curve directly requires some incredibly complex calculus, mostly because the angle of the push is constantly changing all along the curve. But instead of doing all that, engineers use a brilliantly simple trick. They just break the complex curve down into a horizontal component and a vertical component. Step 1, you calculate the horizontal force as if the curve was just a flat vertical wall. Step 2, you calculate the vertical force, which is literally just the physical weight of the water sitting on top of the curve. And step 3, you combine them using the good old Pythagorean theorem to get your final resultant force.
And this is a great way to visualize it. Instead of dealing with the constantly changing curve on a segment, the horizontal arrow, Fx, just pushes against an imaginary vertical plane. Meanwhile, the vertical arrow, Fy, pushes straight down, perfectly representing the weight of the water above the curve. By breaking the actual physics into this simple X and Y grid, engineers can tame even the most complex geometries without breaking a sweat.
Finally, Section 5, Engineering Gates and Dams. Let's see this in the real world.
So how is all of this applied in reality? Well, consider a sluice gate that moves up and down to let water flow underneath, or lock gates that swing open and closed like giant double doors so ships can pass through changes in water elevation. Both of these massive water management structures are entirely dictated by hydrostatic pressure. They aren't just giant, heavy chunks of metal, they are meticulously calculated balances of forces.
For a sluice gate, you usually have water on both sides, so the total force, F, is simply the massive upstream pressure, F1, minus the downstream pressure, F2. Engineers just have to ensure the gate's tracks can handle that difference without buckling. But for lock gates, it gets even cooler. The two doors meet in the middle at an angle. The formula P equals F over 2 sine theta calculates the exact reaction force at the hinges. Because the doors meet at an angle, the massive pressure of the water actually compresses the doors into each other and into the hinge. It's literally using the water's own crushing force to keep the doors tightly sealed. It's honestly a genius application of fluid mechanics to prevent catastrophic failure.
And that brings us to the ultimate application, massive dams. Notice how modern dams often aren't just flat walls, they are deliberately curved. They use all the fluid mechanic principles we've been talking about to efficiently transfer that incredible hydrostatic pressure down into the bedrock and out into the solid sides of the canyon. The math literally dictates the architecture.
Which brings us to the end of our explainer. We've gone from the microscopic zero shear stress of perfectly still water all the way up to massive curving concrete monoliths holding back entire lakes. It is wild stuff. So next time you drive past a dam or happen to see a water gate, I want you to look closely at it and ask yourself exactly where is the center of pressure on that wall. Thank you so much for joining me today, and definitely keep exploring the incredible engineering that surrounds us.